Okay, YouTube, in this video we're going to be looking at the graphs of logarithmic functions, or at least we're going to be looking at the graphing the logarithmic parent functions and then working from there to transform those. So what we're going to do in order to graph these logarithmic functions at first is recognize the inverse relationship between exponential and logarithmic functions. So that is to say that when we look at something like this, which is a purely exponential thing like this, we would say that y equals log base b of x is its inverse, and only to say it's its inverse because if we were to rewrite this exponentially, you could see that this is b to the y equals x. And so the domains and ranges have been switched on these two functions, and the profound thing that happens there is that we know that since their domains and ranges switch, that every point also basically switches completely around. So graphically speaking, when we talk about inverse functions, okay, any functions that are inverses of one another, such as y equals b to the x, which is what you're seeing here. And currently I've selected a b value that's somewhere between 0 and 2. So I'm going to leave it on 2 just so that we have this exponential growth function. But you're seeing that with our graph here, essentially that we have this horizontal asymptote on the x-axis. So let's go ahead and put that in. We say y equals 0. And perhaps we could edit this so that it has a dotted line. We say here is our horizontal asymptote. B to the power of 0 is 1, so it goes through 0, 1. And if we were to look at any other points, how about if the base is 2, 2 to the power of 1, okay, we would get 2. So we would say that 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. We basically have this 2 to the power of x graph. What I want you to see is that as I turn this on then, this is the graph in purple here of y equals log base b of x. And instantly what I want you to notice is that these two graphs are related to one another. And what we want to remember is basically this. When it comes to inverse functions, remember that because domain and range switch, that means that every point on the original exponential function here essentially is just going to take their x and y values and flop them around in order to get x and y's on the other graph. So for instance here where I could say that, you know, at, I guess, 4, let's see if I can get this here, 4, let's see if I can do this here. How about 2 comma 4, we could see that the point 4 comma 2 must lie on the other graph. So the key in graphing logarithmic things is to say that I know that they are inverses of exponential things. So let's try to describe as many characteristics of our logarithmic graph as is possible. So first things first, because all of our points x and y switch around perfectly, then we're going to say that inverse functions are really truly symmetrical about this line y equals 1x. Now this line y equals 1x is really just a line that has a slope of 1. It's in slope-intercept form. So it has a slope of 1 right here and a y-intercept of 0. But all of our points on our original exponential function are going to flop right over here to be on our logarithmic graph. So that being said, we could say, well, what are some things that I always know are true about my exponential functions no matter what? Well, what we know is that exponential functions, or at least exponential functions of the form b to the x, they all go through 0, 1. And also, they all have asymptotes on the x-axis here. And also, they all grow really, 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 really fast. They just keep speeding up and speeding up and speeding up. And so, in terms of graphing a logarithmic thing, how would it relate to the original graph? Well, the original graph has no x-intercept and one y-intercept. Notice that on our logarithmic graph here, okay, we have no y-intercepts but one x-intercept. And instead of being at 0, 1, it's going to be at 1, 0. Now with our other exponential graph here, I would have plugged in 1 and gotten 2 as an output here. So we'd say 1 comma 2, which would have been right over here, 1 comma 2. We would say that 2 comma 1 would just as well have been on this graph right here. And so with respect to points on this graph here, I suppose that we're only going to ever find 2 of them, and one of them is always going to be the x-intercept, and then the other point's just going to be some extra point on the graph. In this case, we would plug in 2, and we'll talk about why here, but we'll plug in 2 because the base of the logarithm is 2. If the base were 3, we would plug in 3. So what we notice with our logarithmic graph is that essentially it is kind of, well, it's the inverse of our exponential graph. So in terms of how it grows, we can see that it's always increasing here, but it grows more and more slowly. This thing will always be on its brake pedal, but never stop increasing how much it goes up. So we would say logarithmic things, being the inverses of exponential things, grow very slowly. Being the inverses of exponential things, go through the point 1, 0. and being the inverses of exponential things, don't have a horizontal asymptote at y equals 0, but have instead a vertical asymptote at x equals 0. And so the last thing we want to mention here is essentially that their domains and ranges have switched. And so that is to say that with exponential things, their domains are all real numbers. All x values work with exponential things, but only y values that are positive here are in the range. When you look at the domain and range of our logarithmic thing, only x values that are in the positive are in the domain of this, but the range is all y values. So you can see that their domains and ranges have switched. So with respect to the parent function for logarithmic graphs, let's just go ahead and talk about the basic characteristics that we want to see. But it says that the graph of y equals log base b of x is shown below for both a base bigger than 1, which would have meant growth in an exponential sense, okay, or a base that's a proper fraction, which would have meant decay. And these are both if exponential, if exponential. When we're talking about our log, okay, it's the inverse of an exponential thing. And so it's going to behave a little bit differently, but we'd say for bases bigger than 1, which is this one that you see over here on the left, base bigger than 1, and for base that's a proper fraction, we would say that y equals log base b of x is given as these red graphs that you see right here. So it says because the graph of y equals log base b of x and y equals b to the x are inverse functions, then the graph of y equals log base b of x is the reflection of the graph y equals b to the x over the line y equals x. And so we can see again, this line y equals x is this line that has a y-intercept of 0 and a slope of 1, but we can see that our graphs reflect over these. So at least from this image here that I pulled from the book, actually, you can see that all the book cared to represent was the fact that your exponential functions, b to the x, they go through 0, 1, and they grow extremely rapidly, okay, from left to right if b is bigger than 1, but they decay from left to right if b is a proper fraction. So both of these graphs go through 0, 1. We've got growth and we've got decay, but they're both reflected over this line y equals x in order to get our logarithmic functions here. So our logarithmic functions, things that we want to say about log functions. Log functions. Okay, I'm going to use the word grow here loosely, but we'd say grow slowly out on the right side. On the right side, these things grow really slowly. So you want to have a graph that the slope is always kind of tailing off to become really close to a slope of 0, okay? And so other things we want to say about this, in terms of the domain of logarithmic things, you can see that it's going to be all x values greater than 0, but the range, unlike exponential things, is going to be all real y values. So you can see the domain and range have switched, okay? We want to say that there is an x-intercept at 1, 0. Now this is true if this is just y equals log base b of the x, log base b of x. But we say the x-intercept is at 1, 0 there, and then we have a vertical asymptote, and that vertical asymptote is on the y-axis, and we're going to give this an equation at x equals 0 here. Okay, so we want to maybe add that in here. X equals 0 is our vertical asymptote here, x equals 0. So what we're going to do is we're going to graph our very first logarithmic parent function. And so in terms of graphing the logarithmic parent function, here's what I'm going to suggest that we do first. 1, find f inverse of x and graph it. So essentially what I'm going to tell you is that because y equals log base 3 of x is logarithmic, and we're really good at graphing exponential things, what we're going to do is, just in a different color ink here, we're going to switch our domain and range, and we're going to find the inverse of this. So because all I need to do in order to get y by itself here is to rewrite this into exponential form, we could say that not y equals. I really want to write y equals, and it will be, but we should do our circular notation here. We say 3 to the power of x equals y. So in other words, y equals 3 to the power of x. So what would we know about this graph right here? Well, we would know that it has a horizontal asymptote, if it's exponential, on the x-axis, y equals 0. I know that if we were to make a table of values here, let's go ahead and do that. If we were to plug in -2, -1, 0, 1, and 2, we would say that 3 to the 0 is 1, 3 to the 1 is 3, 3 to the 2 is 9, and going backwards, 3 to the -1 is just 1/3, 3 to the -2 is just 1/9. And so with this graph here, we could see that it would look something like this here, where we say 1, 3, and 2, 9. But our exponential function would be this right here. So I'm just going to be clear on this. I want to label this with what it is. This is not f of x. This is f inverse of x. This is our inverse of the thing that we're actually trying to draw. So what we could see here is on this graph, if our graph looks like this, then what I'm going to do is I'm going to put in that line y equals 1. And so we would say starts at 0, 0, goes up 1, right 1. You know, here's up 1, right 1, up 1, right 1, up 1, right 1. We get this line y equals x. And we want to make sure that we do label that. We say y equals x. But our graph would be reflected over this. So what that would mean is, at least for our asymptote situation, we would have a vertical asymptote on the y-axis. And we're going to label this. We say x equals 0. Other points on our graph, well, what we could really do is we could just say, well, then if this is the inverse here, then really what we're doing is we're saying that all of these points switch around. So we have 1/9, comma, -2, 1/3, comma, -1. We have 1, comma, 0. We would have 3, comma, 1, and then 9, comma, 2. So to graph these in, starting with the most important one, which is, in my opinion, 1, 0 here. We say 1, 0 is on all of our logarithmic functions here. Then we would say, how about 3, 1, okay, 9, 2. But we also had 1/3, comma, -1, okay? And we also had 1/9, which is really close to the y-axis here, comma, -2. And so we get this function here that crawls up along our asymptote and then grows slowly, 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 more and more slowly, slower, slower. So you're flattening out. And we'd say that this is f of x right here. So in terms of our domain and range, looking at our domain, we say, well, what x values does this function f of x cover? Well, it looks like it covers all x values that are positive. It never gets to an x value of 0. And in terms of our range, we would say it looks like it goes from -infinity to +infinity. So we say all real y values. So the way this is going to work is this. Number one, we found the inverse and we graphed it. Number two, we reflected graph over the line y equals x. So that means switch your asymptote, switch your intercept, switch all the points x's and y's around, and then check out the domain or range. Cheers.